Welcome back, part-time gardeners, aspiring full-time computer touchers, and fellow LeetCode grinders. Back once again, LeetCode daily grind number 3 or 4. I can't tell. I'm becoming delusional. Different setup, also different fit. I'm not wearing the same clothes I was wearing yesterday. So yeah, no new problems today, so I'm just going to be doing some old problems again. The algorithm has not yet blessed me with any new problems to do, but 20-minute timer as usual, go through the problems. I'm not really going to try and teach them, but teaching's pretty cool. But I'm just going to go through it as normal, kind of like, if I was like in an interview or something, but I wouldn't say it's exactly for interviews, but yes. Also, yesterday I posted a video or description. Challenge is also partly inspired by Ivan Jurek, squat grinder extraordinaire, squatting every day. So, in the essence of trying to keep something similar in tow, LeetCode every day. So, yeah, I'm just going to jump into it. Start the timer. Also, I get in the right mindset though. Okay. So remove duplicates from sorted array. You have no goal time or space complexity, but I'm pretty sure this time complexity required is going to be linear time with constant space complexity. You have function remove duplicates with nums. You have an array of numbers and we're going to return a number. So given an integer array num sorted in non-decreasing order, if it's non-decreasing, then it's only ascending. Move the duplicates. Let me move this. In place such that each unique element appears only once. So we're basically deduplicating an array. In the relative order, the elements must be kept the same. But if we're deduplicating the array, we're going to have only unique elements remaining, and if it's sorted in non-decreasing order, we don't have to keep the elements in relative order since they'll be already sorted in ascending order. Since it is impossible to change the length of the array in some languages, you must instead have the result be placed in the first part of the array nums. Okay. More formally, if there are k elements after removing the duplicates, so if we remove the duplicates and there be k elements remaining, those must be the distinct elements remaining. So k is the number of distinct elements or distinct numbers in the array. It does not matter what you leave beyond the first k elements. Makes sense. Return k after placing the final result in the first k slots of nums. Do not allocate extra space for another array. You must do this by modifying the input array in place with constant memory. So if we have 1, 1, 1, we dedupe. We have 1, 2. As there are 2 distinct elements remaining, we have 2. We return 2 distinct elements. We return k, which is going to be 2. So we can do this by keeping track of the duplicates with the two-pointer method, or I guess in another way, the sliding window pattern. So if we give a variable called LUI, which will be our last unique index, which is going to start at 0, and then our second half of the window, which is actually going to start at 1, and usually starting at 1 helps with using the sliding window pattern. And if num sub I does not equal num sub LUI, right, then we want to LUI plus 1 because it's going to be our last unique index. We're adding 1 to it to preserve at least one of the duplicates, because there could be more than one, but we want to keep at least one, right? And that's what this increment is going to do. And then we're going to swap I, right, into this incremented LUI. And then we're going to return LUI plus 1. So this looks good to me. just running it in my head real quick. If we have 1, 1, 2, we're going to set it 0. I is going to be equal to 1. Going to nums.length, which is going to be 3 of num sub I, which is 0. Num sub I, which is 1, does not equal LUI, which is 0. So 1 does equal 1, so we skip this case. Increment LUI. Now we're at LUI equals 2. Num sub I, which is 0, does not equal num sub LUI, which is 2. 1 does not equal 2, so we increment LUI. LUI to here. Swap 2 into LUI, and then we have the number of duplicates. Well, we only incremented LUI once. So LUI is actually going to be 1. So we have to add 1 to it, which is what we're doing here, and we should get the correct number of distinct elements. So it looks good. And the time complexity is going to be linear time since we're iterating over the array nums. So it's going to be linear time with constant space. So this one is convert a sorted array to binary search tree. There's actually no goal, time complexity or space complexity for this, but I know that the case which we solve for is actually linear time with log of n space. So we have this class tree node. This is the definition or a class declaration for a binary tree node. We have the value which is stored in the node and pointers to the left and right subtrees, which are also defined by tree node. Our constructor lets us take the value. Our constructor lets us take the value of the node. Our constructor lets us input a value into the node, while also setting the nodes for the left and right tree nodes, which makes sense. So we have function sorted array to BST. So we have a sorted array that we want to convert into a binary search tree. Well, we know that, and this might, well, let's read the problem. Given an integer array nums, where the elements are sorted in ascending order. So for this array, numbers are sorted in ascending order, converted to a height balanced binary search tree. The height balanced part just basically means that when we have the option to choose a node or declare our pivot, we're going to declare it as the center of our range. Height balanced binary tree is a binary tree in which the depth of the two subtrees. Height balanced tree is a binary tree in which the depth of the two subtrees is never the depth of the two subtrees, every node never differs by more than 1. Height balanced binary tree is a binary tree in which the depth of the two subtrees. Depth is defined as what? Depth of the two of every node never differs by more than 1. Never differs by more than 1. Which makes sense, because if you look at the depths here, they're not differing by more than once. I kind of want to interpret the height, which means that the height of the, I guess the height is for an entire tree. You get the depth. Depth may be the how far down from the root node a node is. So maybe the depth of this node 9 here is 1. But basically we have an array which is sorted in ascending order, and they want us to convert it to a binary search tree, which makes sense. Maybe something that's important to note is that a binary search tree in depth first search, an in-order traversal of a binary search tree produces an array in ascending order. So if we do a binary search on, or binary search like operations on a array, we can produce a binary search tree. So what we can do is call this function helper. I'm going to go from 0 to nums.length -1. And this is similar to when you do a binary search over an array. And we're going to pass in nums. So you need to keep track of that or have access to it so we can assign values to nodes. And so left is going to be set to number. And right is going to be set to number. And we're going to declare this array, which is going to be a number array. It's going to return either a tree node or null, right? But when do we want to return null? Well, if left is less than or equal to right, then that's how we know we're good to calculate the pivot, right? Otherwise, we're going to want to return null. If these ever pass each other, it'll be impossible for us to calculate a correct pivot, right? So I'm actually falling out of frame. But another angle, right, is that we have, not another angle. Now I have to calculate the pivot or the midpoint, and that's usually the left side, right, plus the math.floor just because it's JavaScript. We'll do right minus left over 2, and then we'll do if I actually just got confused. Right, so once we calculate the pivot, we're actually good here. What we're gonna do is we're gonna create a node, right? Because we're assembling the binary search tree. I got confused because I was gonna go into actually writing a binary search. We're gonna create a tree node, right? And this value is gonna be set to the nums sub pivot. Right, so we're gonna set this value up here, right? And then we're gonna say, hey, node.left is also gonna equal to the continuation of this binary search. So what we're gonna do is gonna say we're from left to pivot -1, and we're gonna pass in nums. I'm going to duplicate this line, and we're going to go from right. Oh no, we're going to go from pivot +1 to right, and then we're going to return the node. And so what actually ends up happening is that we actually end up placing a node when the values are the same. And if we go through this in our heads with a simple smaller array, we'll be able to see that. So if we have, let's just say -3, 0, and 9, then what we can do is just run the code, right? So we're going to call helper going from 0 to nums.length, and nums.length is going to be 3 minus 1, which is 2. So this is from 0 to index 2. 0 is less than 2, right? Calculate our pivot, it's going to be 2 minus 0, which is 0, over 2, which is 1, plus left, which is 0, which is 1. So we get index 1. So we're going to create a new node with num sub pivot. So we're creating a new node with value set to 0 on this node. Well, then we want to calculate that same function except for the left subtree. So we're going to go from left to pivot -1. Pivot -1 because we already handled this node in the center, which would be 0. So now we're going to go from left, which is 0, to pivot -1. Well, pivot was 1. If we -1, it's going to be 0. So now we're back up here. Is 0 less than or equal to 0? Well, it's equal, so we're going to create another, we're going to calculate another pivot. Well, is math.floor of 0 minus 0, which is 0, over 2, which is 0, plus 0 is 0, right? So we're going to create another tree node with num sub pivot. Well, our pivot is actually index 0. So index 0 is going to be -3. We're going to place it inside the node, right? Then we're going to calculate the left node for this 3, this negative 3. It's going to go from left, which is 0, to pivot. Pivot is 0, so pivot minus 1 is going to be negative 1. So now we're back up here again. Is 0 less than negative 1? It's not. We return null. The left subtree for negative 3 is going to be null. Well, we're still in this function, so calculate the right subtree. Well, pivot plus 1, pivot is 0. 0 plus 1 is 1. 1 is not less than or equal to 0, right? So we're going to return null for the right-hand tree. Well, then we're going to go all the way back to 0 up here and go back to calculating the right node. So pivot plus 1, our pivot was 1, plus 1 is going to be 2, right? So we're going to go from 2 to 2, right? Because right is going to be equal to 2. So when we first called the function, we called it going from 0 to nums.length minus 1, which is 2. Well, 2 does equal 2. We calculate the midpoint. 2 minus 2 is 0 over 2 is 0 plus left, which is 2, is 2. Create a new tree node with the num sub pivot. Index 2 is 9. Create a new node here with this 9. And we're going to have the same null cancellations for the same thing that we had for negative 3. This is just basically going to produce 2 null trees, which is what we want. And then we return the node, right? So if we run this, we should be good. I'm going to delete this line, but I just want to run it in my head real quick just to make sure there's no syntax errors, hopefully. That's 1, passing in nums, it's an array of numbers. Return null, pivot left plus math dot floor, right. Makes sense. I need to slow down just so I don't want to make any lapses in logical error or get into the habit of writing things off too quickly as correct. So I want to go slower. Time complexity of this should be linear time because we have to visit every number in the array. But I don't know if that actually tracks for me though. If we have to visit every number in the array because of the binary search, it's linear time because for n numbers we have to do n operations. Yeah, I think that's true because when we actually place the number in a node, we're actually calculating the pivot. Yeah, I think there are that many operations. Log of n. The space complexity, I don't know if I'm exactly convinced that the space complexity is log of n. I get it's a binary search, but I don't understand why the space complexity is log of n. Yeah, it's hard to put my finger on why the space complexity is log of n. We're not searching for a number, but on each binary search, we're having the search space, and we're calculating the pivot. Binary search is log n because we're having the search space on each iteration, but it's unclear as to why this should be log of n space complexity. I'm saying log n because I know at the end of this solution, it's going to say log n, but I don't understand why it's log n. This is log n because the tree is height balanced. Height balance just means we pick the center of our range as the pivot on each iteration. I kind of want to see. I mean, there's not too much that's different from this iteration versus my iteration. There's only 1 minute and 53 seconds left. I'll take it as a pass, but I'm not sure why that's log n. And I'll do one last one. So we have min stack in 140. Design a stack that supports push, pop, top, and retrieving the minimum element in constant time. So I think we did this with 2 parallel stacks yesterday, and I like that solution because I think it's the most intuitive. So that's what I'm gonna do here. I don't know if there's any extra overhead that could be minimized by using the same array, but when they ask us to push an element onto the stack, we're just going to push val onto the stack, and we'll come back to implement this later, but it's going to involve some code with min stack. When we pop, if this dot stack dot length does not equal 0, then we want to pop the end of this array and the end of min stack. And if we want to check the top, well, we can only check the top if the array is not empty, right? If it's not empty, then we can return this dot stack sub this dot stack dot length -1, right? Because the last element in the array is always a length -1. Otherwise, it'll return -1. I've done this problem a few times, and it never tells you what to return when. Yeah, they always say that it always operates on non-empty stacks. So yeah, it's kind of, it is what it is. We'll return -1 anyway because our type says we're going to do that. And when they want us to get min, well, we'll say, hey, if this dot min stack dot length does not equal 0, then we're going to return this dot min stack. So this dot min stack dot length. Otherwise, we're going to return -1. Right? Now that we have the min stack, when we're pushing an element onto the stack, we're going to want to, when we're pushing an element onto the stack, the min stack, we're going to want to do something different. All right, so we're always going to want to push something onto the main stack, but if this dot stack dot length equals 0, right? Let me just set up a key binding real quick. Then you want to push this dot min stack val, right? If this is the first element we're putting into the stack, then the min so far is just going to be this element, which we're pushing to the stack. But if we do this dot min stack, if it's not the first element in the stack, I mean, if the stack isn't empty, then we want to take the math dot min of val and this dot min stack dot length -1, so we can keep a running sum, the smallest element we've seen so far. So this should give us constant time on all these operations. Push, pop, and top you actually get for free, but it's get min that's a little spicy to implement, which we're implementing here. So we have 2 stacks. We're going to push this onto the main stack. If the stack isn't empty, then the first minimum value is just going to be the value we pushed on it. Otherwise, we're going to do min stack dot push the smallest value between the value we're pushing onto the stack and the smallest value we saw so far. It's going to be this dot min stack sub the last element in the array, which is min stack dot length -1. Pop. If the stack isn't empty, then we're going to pop the top off both stacks. Otherwise, if we want to do top, we want to check the top. Well, if the stack isn't empty, then we'll check the top. Otherwise, we'll return -1. To get the minimum, we'll check if the minimum stack is empty, and if it's not, we'll get the top element on that minimum stack. Should be okay. It's not okay. Ah, it's the same mistake I made yesterday. You don't have to do this. I don't even think you need this constructor. I think you can do that. We'll see. Okay, this is just wrong. Saying the whole thing is empty. minStack.push math.min of value dot length. But if we pop an element off the stack, if the stack isn't empty, then we pop element off both stacks. This dot stack dot length, if we want to get the top element, we have to check if the stack isn't empty. -1. If we want to get min, yeah, the rest of the code looks fine to me. I think something's wrong with my syntax up here. I don't think I have to do this. Or maybe I do. Maybe I don't understand JavaScript at all. Yeah, how do you... I'm having a brain fart on this. Yeah, this seems a little, like, very redundant. I don't think I should have to do this. Yeah, I think I'm farting on this crazy. This.stack.push is unclear if the stack is... Oh my god, I'm not... Oh man, this is bad. When I'm only pushing on the min... No, wait. No, this is fine. I'm pushing onto the main stack as well. This seems strange. I might be doing anything here. Yeah, this is strange. Let me take it. I need to slow down. I'm pushing onto the stack. They're passing in a number. The number is val. This dot stack is an array, and I'm pushing the value onto the array. All my values are null, so something's got to be wrong with push. The stack is empty, and I push the value onto the min stack. Otherwise, I push the minimum of the value that we're pushing and the last element in the min stack. When I pop. If the array isn't empty, then I pop off both ends. If the top element, if the stack isn't empty, I return this dot stack subscript to get an element in the array dot length -1. Then I do get min if this dot min stack dot length does not equal 0. Yeah, I'm might be having a bit of a brain fart on this. Yeah, whenever I get stuck, I just start questioning my entire... Yeah, I just have to check my other submission. This was yesterday. Yeah, you can just do it like this. Okay, I'm actually not seeing what the difference is between these two implementations. Yeah, this is basically... Yeah, I'm absolutely dumbfounded right now. I'm completely confused. I'm finna just start copying and pasting code in. I just did this one yesterday. I mean, some of the code is slightly different, but it's unclear. I think I'm missing something like so basic. I'm getting nulls and nons. I'm just gonna start copying and pasting entire blocks. .minstack.push math.min of val, or this.minstack. So this.minstack.length minus 1. Wait, that literally makes no sense. I'm not seeing the difference between these two lines. I'm pushing in both cases. The reverse of this case is still true. If this dot stack, oh, I see what's going on. It's a slight change, but it's because of the order. In this one, I check if the min stack is empty before pushing onto the min stack as a default value. The problem is though, in this one I check if stack is empty. But I just push on to stack, so I never actually put the initial value into the min stack. I see. Half of the problem I think is because when I did do this problem before, stack and min stack are essentially interchangeable in every function because they're parallel arrays. They always have the same length and the same number of elements within them. It's because when we push onto this one, we push onto the other one. But this is the one function in which the use is not interchangeable. The change that actually makes the difference and should make this work is if I change this from stack to min stack, and this should run. Yep, there we go. Okay, there we go. Is that a pass? Is that a pass? I think that's a pass. I think that's a pass. But thank you for tuning in, my dudes. Be back again tomorrow on June 17 for another daily LeetCode banger.